pick back up for our second speaker today, and he is David John Gagne, and he's a doctoral student at the University of Oklahoma. Right now he's out at NCAR doing some work. He's got some pretty diverse interests. In addition to machine learning techniques and weather prediction, David's interests also include, I believe, hail size prediction, short-range forecasting, and I think you're doing some solar energy work out here. Anyway, he's going to talk to us about a geeky topic today, given his Oklahoma roots, in terms of presenting on severe weather forecasting and its integration with Python. And without any further ado, David.
Thank you. So good morning, everyone. Today we're going to be talking about severe weather forecasting and how Python and data science tools can fit into this long and fascinating field. I'm from Oklahoma. The most recent tornado I've seen actually came from Colorado, just north of Longmont. It was an EF3 that went actually from east to west and tore some houses, but it was also picturesque and no one got injured, thankfully. So our overall goals for the session, first we're going to show you some of the Python products from the severe storms community that kind of highlight some of the different areas it's being used in. And then I want to talk about data science, define it, and tell you how it can be integrated into the severe weather forecasting process. Then discuss some of the Python libraries and how they can also fit into the severe weather forecasting process. And introduce my own library I'm called Hoggleslog, to do hail forecasting and other kind of severe impacts forecasting that mixes the two areas. And finally, we'll do an interactive activity where you can kind of see some of the power and do some data science-y activities within IPython notebook. So a little bit more about me. As Steve mentioned, I'm a PhD student at OU and visiting NCAR RAL. My bachelor's and master's also came from OU. And along the way, my main advisor is Dr. Amy McGovern, who's a CS professor who's collaborated with a lot of meteorologists and worked on various severe weather problems, but with a more data science spin to it. I've published in both meteorology and machine learning journals and conferences, so I've kind of worked both sides of the area and learned to speak both languages in a way. I've also served as a student member of the AMS AI committee and have been primarily a Python developer since about 2008, but I've also used Genpack, MATLAB, Java, IDV, R, and JavaScript extensively. So I'm kind of familiar with the general ecosystem that meteorologists are working in software-wise. So Python has really taken the severe weather community by storm, if you will. A lot of different organizations have been embracing and actually making operational Python products. So the SPC has a number of Python developers. Products they have made include this severe weather climatology map. I think some of their new severe reports page has some Python bindings in it. A lot of back-end stuff is using Python. It's been very much embraced by that organization. Here at NCAR, if you've seen the new 3-kilometer storm scale ensemble from NCAR, all of the graphics are being made with Python. It's all matplotlib and basemap that run, and basically all this is also not just running on a desktop, this is running on the Yellowstone supercomputer. So Python isn't just for your little things, it's also can be scaled up and do big things too. Back at OU, the nchart package has been ported to Python through a project called SharpPy, which some of my friends have been heavily developing and made it into a very nice GUI product that I recommend you check out. And then over at the Argonne National Laboratory, so ARM and a whole bunch of folks there, they've developed a radar toolkit called PyArt that in addition to displaying radar data, also has a lot of cool algorithms that are written in Python, like this velocity de-aliasing tool. So that's Python, the severe weather community. It's gotten pretty big. It's a lot of good use, especially on the display side of things. So now I want to jump over to data science. So what is data science kind of in a nutshell? It's a term that gets thrown around a lot. You hear big data science, big data, deep learning, all these in all these news articles recently. I like to kind of define it, and it's sort of similar to the Wikipedia definition. It's basically the process of extracting useful knowledge from large amounts of data. Alternatively, if you're a little bit more cynical, it's the latest in a series of buzzwords going back from AI to data mining to analytics to informatics what have you, that describe kind of a more computationally intensive radical statistical analysis as well as modeling prediction. So data science has kind of come to encompass these a whole bunch of different sub-areas in the computer science, AI, statistical worlds that have basically come together to make really interesting data-driven insights. So we have machine learning from kind of more from the AI community, databases and data management, which is a lot of what we're talking about here. But also like interactive visualizations, some of the cool stuff you see on things like the Upshot or 538. We also have image processing, so like things like trying to identify cats in images or Google image search or some of the other. There's a lot of cool stuff out in this area. And then analytics. So on the business side, that's usually trying to get some insights about if temperatures are above 75 and the stock market is doing well, then you should sell umbrellas or something like that. And one question that sometimes comes up is data science just applied statistics? And my argument, and some people say yes, some people say no. I'm on the no side. I think it offers something special. And one good paper on this is by Leo Breiman, which is about statistical modeling the two cultures, and kind of describes how the data science approach is more focused on trying to get basically improved predictions, improved products, get more useful insights moving forward. Where statistics, while data scientists tend to use a lot of statistical methods and try to make their methods more robust with statistical techniques, they don't necessarily share the same statistical culture and use different methods and sometimes are a little bit more adventurous with their assumptions, for better or for worse. So is data science like a new thing? How much has it actually gotten into severe weather forecasting? Before I get into that, why is data science in severe weather forecasting? Why is it needed? Why is it important? Why can't we just keep doing the same things we've always been doing? Well, one problem is, on the one end, we have convection aligned model ensembles. So our grid spacing is getting finer. We're seeing individual storms, and we're generating lots of these models hourly, every day, filling up terabytes and terabytes and petabytes now of storage with all these model runs. And the problem is that with all this data, it's getting increasingly hard to analyze unless you have some kind of techniques that can encapsulate and find what parts of this grid are particularly useful and find a way to visualize it for the meteorologists so that they can actually make better forecasts. At the other end of the spectrum, we have remotely sensed gridded observations. We have gridded radar data like the NSSL multi-radar, multi-sensor system. We have GOES-R on the horizon. Even on the observational sets, we have Mesonets and MADIS and all these other bigger observational data sources coming in that also present some similar challenges. At the end of the day, though, we want to combine both of these and produce useful forecasts that we can guide our forecasters or send to the public directly and provide them useful information for the hazards that they're actually experiencing. So what are some of the efforts currently going on? This is not exhaustive by any means. There's a few recent examples I thought were kind of cool in the severe weather community. One out of the SIMS of the North, University of Wisconsin, is an algorithm called Prob Severe, which mixes radar data, satellite data, and a naive Bayes algorithm to actually identify growing convection and see where a storm is occurring, or see it and predict, basically use all the different data sources and to try to tell you if the storm is going to become severe very soon. And it was very confident that these storms would become severe, and the associated tornado warnings verify that. Out of the MIT Lincoln Labs, they're also a heavy user of machine learning techniques, and they've trained a random forest to take lightning and satellite data and basically make simulated radar products over the ocean. So there's no radar sites out in the middle of the Gulf of Mexico, but look, we have this very realistic-looking radar image that's been almost seamlessly merged with actual radar data from Florida. And this is using techniques that we're going to kind of cover today. One of them is a random forest. Another cool approach of the random forest technique is actually doing some more of this data merging and basically predicting aircraft turbulence. So you see these aircraft are flying through this line of severe storms, and the random forest algorithm tell them, hey, this is not a good place to fly. So, and some of these are either running operationally or very close to being operational, and are in the process of being very soon. And this is just a subsample of what's going on out there. It's growing, it's getting out there, it's showing good results. So now we want to combine these two areas. So we have our Python libraries, we have our data science stuff. Where do we go in this like sea of different Python libraries in order to actually do some of these different tasks? Well, if we want to read our gridded data, we have a whole series of libraries out there. So we have netcdf4 for Python, pygrib, xray, pineo, scipy, all kinds of other stuff out there too. Xray. If we want to identify threat areas in our data, we want to actually kind of do some, actually look for, like, try to sort out all these big grids and take it from big data to kind of small data. There are algorithms in SciPy, scikit-image, and scikit-learn that can do this. Once we want to actually derive and calibrate some forecasts of like hail or tornadoes or other severe threats, we can use algorithms from SciPy, pandas, and scikit-learn. For visualizing our forecasts, Matplotlib and Basemap are a great source. If we want to make it interactive, the Jupyter Notebook system is very, very good at that. And finally, we want to verify. We want to show that we've actually improved on the raw data, the raw forecast. So we can use statistical packages like pandas, NumPy, SciPy, scikit-learn, and actually verify. So what are some of these packages? One in SciPy, for those who aren't familiar with it, it's a collection of general scientific computing tools. So it has everything from basic statistics, so it has all the different parametric distributions you could ever want, to a pretty full image processing library, and it can also do interpolation, so you have splines and linear interpolation and all kinds of other cool stuff. And a lot of it calls some of the old Fortran and C libraries that have been like tested over decades and optimized a lot. So it's a very powerful, very useful library. It's part of the core scientific Python stack. Pandas, we kind of heard yesterday from Stefan's talk. It's another powerful data analysis library where you can load in your ASCII tables or Excel files or even HDF5 or SQL databases and load them to a data frame and do all kinds of fun statistical analysis and plotting just within this library. Scikit-learn, which most people here are probably not familiar with, is a Python machine learning library. So basically, with machine learning, the idea is you give the computer a bunch of data and you give it a model and you tell the model to train on the data to produce a certain kind of prediction. The scikit-learn library, the idea of is to make that really easy and to support a lot of the libraries that have shown through the 20 or 50 years of machine learning research to really be good, robust libraries and have been used widely. So it's everything from your basic linear regression to decision trees, random forest, some of the newer stuff like relatively newer stuff like gradient booster regression, support vector machines. You can do clustering in it. You can do PCA. Analogs. It's pretty fully featured. For my contribution, which is kind of still in the alpha testing stages and very initial work, I'm calling it Hoggleslog, which is an object-based severe weather forecasting Python package. It's named after the popular Dutch snack of sprinkles and butter on toast, which may sound unusual to American taste, but apparently is pretty good and looks really cool. And all the little sprinkles scattered on top of the toast kind of reminds me of all the little storm objects stacked on top of each other. So if you're familiar with like objectivity plots and the Ensemble Max ones, it kind of reminds me of that a little bit. So if you haven't already, to download it, first, assuming you've done all the pre-installation stuff, go ahead and do source activate workshop scikit. And then if you haven't cloned it yet, you can clone the repository from my GitHub page, or you can download a zip file from the same page. If you're a Windows user, doing the zip file is a lot easier than trying to install Git. And then once you have it installed, you just go inside the first directory and do python setup.py install. I'll give you a quick demo of how to do this. So I have the. See. So I've downloaded the library already. I want to actually go into the right environment, so we do source, activate, Workshop scikit. Ta-da! And then, so we're in that library, and then we want to install. Once we have this downloaded, we want to install all the stuff into the Python installation. So you see a bunch of things go by, and once it gets to finishing processing dependencies, that means you succeeded and everything is good. And it should go really fast because everything should be installed. If not, then put up a red sticker, and hopefully someone can come and help. It looks like, yeah, if you're having problems like base map or some of the other heavier duty ones, there are ways to get around that. So once that's installed, you'll want to go into the demos directory, and you'll notice there's one thing called Unidata Users Workshop 2015 IPyMB. So we just open the IPython notebook. And it'll take a second. Then you'll get this page, hopefully, and click install. Or click and it'll open up. And you should see something like this. So make sure I didn't miss any steps. Okay. So now we'll switch over to the interactive portion of the presentation. Is there anyone has everyone managed to get to this point? Any problems? I see sea of greens. Oh yeah. Okay.
Back up one step or two.
Yeah, I'll give everyone a couple minutes, and so now you can either read through the introduction. I'll kind of summarize for you. Basically, we're kind of in this area of big data and also of larger severe weather data sets. And basically, with all this data available, one of the things one of the risks that can potentially come into this process is that we have all these cool automated tools. So why not just take the forecaster job and let the computer do all the forecasting? But there is another way to do this. We don't have to just let the computers take over. We can, by smartly designing our computer tools and building better visualizations and better techniques and educating our forecasters on how to use these techniques, we can kind of take a combined approach. So you have forecasters that can utilize these tools and go through the data, not be overwhelmed by everything being thrown at them, and then kind of find the hazards, investigate them with all their meteorological knowledge, and then make hopefully an improved forecast that is better than either just a human forecast with the traditional approach or a purely machine-based approach. And there's a lot of evidence in different fields that show that this can be a very workable model. In the chess community, for instance, there's an article recently about how chess. One of the new innovations in computer chess playing is not just having the computers play each other, but also having humans with the computer on their laptop next to them, telling them moves, but then sometimes saying, "Hey, I don't agree with that move. That seems kind of weird. Doesn't seem worth it. So I'll make my own move." And they actually have cool competitions. And sometimes the mixed hybrid computer and human chess can do some really cool things. So there's nothing stopping us from, if we can do that in chess, there's nothing stopping us from doing that in weather forecasting. In fact, we're already pretty experienced at integrating computer guidance and knowing when it's bad or when it's obviously off the charts or not good in any way. So with these kind of part of the problem though is with these new data science tools coming into practice, forecasters don't necessarily have this education experience. So efforts like this should help lead to them to start getting a grasp of what these tools can do, where their limitations are, and how to incorporate them better into their workflows. So it looks like most everyone, I guess before I move on, are there any questions, comments that people would like to make? All right, full speed ahead then, or we'll go half speed, I guess. Try to avoid the icebergs. So first we want to import all of our different Python libraries. So we're using NumPy, pandas, matplotlib, the datetime library for handling dates, basemap for drawing our maps and doing our map projections. Also, a couple of cool things. One is IPython display and IPython widgets. So IPython has some features where you can actually add even more interactivity than there already is in the notebook. So like once you run a cell, you can do additional interactive stuff like add sliders and radio buttons and other GUI kind of GUI goodness to your cells to allow you to add more fast interactivity to them. And also, you don't have to do additional. You don't have to go and re-edit the code when you want to change a parameter. SciPy, we're using the Gaussian filter to kind of smooth some of the data out a little bit. And then some glob is a cool function. If you're not familiar with it, it lists the contents of directories and can handle like all the stars and stuff that you usually use in Unix LS. So, and then once we have all that, we want to import all of our Hoggleslog library stuff. So one thing we're using is the enhanced watershed segmenter, also a special model output handling library. We're going to be object matching for tracking our objects that we find with the enhanced watershed, and then we want to store our objects in a data class that will actually allow us to interrogate them a little bit more. So we have something called ST object or spatiotemporal object. For this, we're using the model output from the control run of the CAPS 2015 Storm Scale Ensemble Forecast System. The model output is included in the Hoggleslog package, so you don't have to download anything else. But there are some additional files that are, if you wanted to look at like composite reflectivity or I think dew point I threw in there. I put them up on my personal page, which is linked here. They're in a tar file. You can download them and change your paths and stuff and load them in. They also work in IDV too. So if Brian wants to play around with them or anyone else wants to play around with them later, I tested them. They do work, and you can make cool plots there too. So now we'll load the data, and if you see success, the number will come up and just say loading SSEF. We loaded the data. We also loaded the map information. So there's some projection stuff. It handles that and creates all the lat long grids. And we're loading updraft helicity. So 2 to 5 kilometer updraft helicity. It's often used as a proxy for strong rotating updrafts or supercells in the model. So good if you're trying to make a hail forecast. You probably want to know where the updraft is, and you want to know if it's a rotating updraft. So let's actually see what the data look like. So we'll make our base map object, and so this is the full model range of all the updraft helicity tracks. Kind of take a glance at and pick out some interesting features here. So there's some tracks in like central Colorado. Column tracks, because they look like they're kind of these discrete objects. They have these very high values and a really sharp gradient. We also have this longer, kind of weaker one that goes all the way through northern Kansas, and then a couple other ones intersecting it. So, I mean, it looks like there should be discrete storms producing these tracks, but the question is, how do we actually identify them in the data and do it automatically and accurately? And if we want to, so another cool thing we can do is our first little interactive demo. So this is just like a static view of it. But let's say we want to actually like look at it through time. So we have this slider up here now, a certain long range and latitude range, and then we have hour. So I can select the hour, and then I can advance it, and it changed. Update it to the next time step. And so we can keep going, we can like move it up a few time steps. And it's like, it's sort of, it redraws the entire image, but it kind of acts like a pseudo animation that's being done in real time. And you didn't have to edit a single bit of code in order for this to work. So we can kind of see that the track in Kansas as it's going through is just like kind of all by its lonesome, going through in the morning. So it may not be a supercell, may be more like an MCS or something. But then we have additional storms that are forming in Colorado and New Mexico. later in the afternoon. And then we have some storms in Wyoming too. Yeah, ironically, even though the picture I showed at the beginning of the presentation is had a pretty big tornado in Longmont, there were actually no updraft helicity tracks. Maybe some very weak ones in the area around Longmont. So the raw model didn't actually do the best. This particular model didn't do the best job on this day. So go ahead and flip through it. You can also try zooming in on a certain area. So we can look at a smaller range of latitude if you want. Kind of pseudo zooming. Actually, we want and feel free to play around, kind of interrogate it a little bit if you want. Yes. Okay. Okay. Will do.
I think the issue is that some folks didn't get basemap installed.
So for those who didn't get basemap installed, there's a sort of simple fix to this. So in the code where there's where it calls basemap, the easy solution right now is just to comment the basemap lines out, because they're not. It's nice to have it, but it's not essential to the exercise. So for instance, in the first part. So I have this big basemap call. So first you comment it out of the import, like so, and then wherever it's called, first you just comment out the first one and the other sublines. It's a little bit of work, but it's not. It could be much worse. And then usually the only basemap call within is just the basemap.draw states or draw countries or whatever. So you comment that out. And then there's also a basemap call down here, the zoomable one. So, yeah, I have to comment all the. So yeah, no geo lines. If you want, you can add a command called plt.grid to your stack, and it will at least give you lat long lines, so you can kind of see where things are. And then wherever basemap's called, just comment that out, and if everything else is there, it should work fine. Well, you may also need to comment out the load map info, but yeah, if for some reason it's not working for you at all, the alternative solution is to go onto the GitHub page, my GitHub page, go to // Unidata demos, and then Unidata Users Workshop 2015.ipynb, and GitHub will actually render it for you, so you can see the examples and the visualizations that have already been generated. You can't interact with them as much, but you really see what everything should look like, and then we can work on the issues with basemap this afternoon. Is everyone okay to move on from here?
Up to the top of this page.
Are you good? Okay, I guess moving on a little bit to the first kind of data science step. So we have our model output, which basically is stored in a 3-kilometer grid spacing grid. And right now there's a lot of spaces that have absolutely no data in them. So really, at least just looking at updraft helicity, we really shouldn't care too much about what's going on there. It's important for other meteorological variables, of course, but But for our for finding the storms, though, we want to concentrate more on where the actual attractilicity maxima are. So one way to do this is, well, the easiest way to do this is just to like pick a threshold. Let's say I only care about attractilicity above 25. The problem comes in, though, is that now sometimes the just picking a simple threshold results in objects that are like either too large or too small. You might if you have the threshold too low, you have too much noise. If you have it too high, you're going to be missing stuff. So there's been a lot of work to try to find object finding methods that kind of get around those issues and are better at finding what is meteorologically significant or significant to whether domain scientist is using the particular product. One tool in this is called the enhanced watershed transform, which is used for identifying features in gridded data. Especially, it was originally designed for gridded radar data. Backing up, the original watershed transform, the idea of it is to identify a region from an image or grid by first you find local maxima. You see where like the locally highest values are in a big image, and metaphorically, one way to think of this is you have think of like the Hawaiian Islands, and so you have we have the islands that you see above the ocean, but then there's other islands below the ocean, and we can kind of use the ocean as our filter. So we start with like where the current Hawaiian Islands are, and then we can start with them as our local maxima, and then we can drain the Pacific Ocean, metaphorically. And as we do that, more land will start appearing around the edges of the islands. And then new islands will also show up that were originally below the water. And by lowering the water in certain steps, you can actually start adding land on and identifying it with certain islands as opposed to other islands, and then identifying new islands that are shorter. And you can basically keep doing this until you drain the entire ocean and then find how everything is connected. Or you can stop at some lower threshold and say that these are my objects. This has worked really well in a lot of applications. For meteorology, sometimes this process can result in some unrealistic-looking objects, and things that we wouldn't call storms. They don't look blobby enough for us. So, like Schwann in 2009 came up with some additions to the watershed algorithm to kind of address these issues. One is first they quantize the data into different steps to kind of speed up the process. Then instead of using like a minimum value threshold, instead they use a size threshold. So you look at how many pixels are associated with a particular object, and you stop growing the object once it reaches a certain pixel size. Then you also have a kind of a relative intensity threshold idea parameter too. The idea of this is, so if we have a storm that has like 70 dBz and we want to capture like the core of it, you only have a relative range of values of like 20 or 30. Whereas for like a smaller storm, then it might not reach that threshold or might capture a larger part of it. And so there's a lot of different parameters you can play with, but you can use these to identify storms at different scales, identify things at different intensities. And it's pretty powerful in that respect. But it does require a lot of tuning parameters. So, and one thing we like to complain, especially the observational people like to complain about meteorology, is that models have too many parameters you can tune. So for this first exercise, which I'll give you all a few minutes to play around with, we're going to do some manual tuning, which is what a lot of researchers do anyway. So you pick a model time step and then tune the parameters until the objects look reasonable or unreasonable. You can try to break it. There's some interesting edge cases here. So run it. So we see all these little dots, which are objects identified from the enhanced watershed transform. So, what parameters can we tune? Well, one is the size parameter. We can try to make the objects make the maximum size potential a lot bigger. Then we'll see if it'll take a second to see it's starting to grow. And yes, there wasn't much changes, but that's because we had the delta set very low. So if we also increase the delta quite a bit, we should also see some
you see some changes, like this object got a little bit bigger, this object is getting bigger. And stop. So one thing you can do, I'll give you probably like, let's see, what time is it? Give you a few minutes to kind of play around with it, or like maybe like 5 minutes or so, and then we can, and you can see, like play with the parameters, try different times, and if you get anything interesting, show your neighbor and talk about it, and then go for a few minutes and see what happens.
Is there any significance to the color scheme used?
No, it's set up to be random, sort of random. I was trying to make it so that you can actually determine if objects near each other are actually different colors. Or sometimes works, sometimes the combinations don't always come together well. You can also, if you want to try different color schemes, there are ways to edit it. So if you want to use some of the, let's see, where is it? So I used set 1 for this one, but you can also use like my go-to is YL yellow, orange, red, at least for quantitative data. For this, it doesn't make as much sense. So you see some are yellow, some are orange, some are red.
Color palettes.
Yeah, yeah. If you look at the Matplotlib documentation, they have a whole fun list of them.
Gotcha. Thank you.
Yes. It kind of depends on your application. At least in the enhanced watershed literature, usually the big distinction being made is trying to find an individual storm, like supercells versus like a line of storms. Because sometimes you can get a line of storms where they're kind of connected with each other, and if you set your thresholds too low enough, then the storm object will be connected based off of the threshold. Yes. Yeah, or if you have two cells that are close to each other and they get merged together, sometimes that might be. It depends on your application. Some people actually care about the big cell, the big line. Some people care more about the individual cells. For this activity, we want to care about the individual cells. Since we're already at 11:22, I'll kind of move on. So once we find our objects, we can we pick some parameters, we can run and find all the objects through time. And it gives you a helpful little progress bar here. And also notice this is all pure Python, and it's all actually running pretty fast. It only takes a second or two to do this object finding on I'm not giving it this little subset, I'm giving it the full CONUS 3-kilometer grid. So you think you have to go all the way down to C or Fortran to get this kind of speed. It's not necessarily true. If you smartly design your Python, you can get pretty fast code. For the sake of time, we're not going to do too much on object tracking, but part of the idea is once you have your objects identified
often there's additional information to be found by being able to track them through time. Like you want to know about the growth and the decay of them. So I have an additional set of code that kind of allows you to do basic object tracking by comparing the centroids of the storm objects with each other. And then I also added two kinds of distance calculations. One allows you to just looks at the centroids, finds the minimum distance, and then optimizes it. The other will estimate the motion of the storms, and then shift the storms from one time step to the previous the locations to the previous time step, and then do the distance calculation. And that one actually, so as an example of this, so this is with the shifted distances with the motion estimation. And then you notice everything's pretty well connected. You have track here, track here, track here, and they all look pretty reasonable, no big jumps. If we shift to just regular old centroid distance, suddenly all these tracks get broken up into where they're not tracks anymore. They're just like little segments, depending on how close they are. You can increase the maximum distance in some cases, and it connects some of the tracks. But then we get things like this, which is like a line jump, where these should be separate tracks. Storms don't suddenly go like that and then keep going on their merry way. And then if you have a lot of fun, you can change the max distance to really large, and it'll connect all kinds of things that really shouldn't be connected. So constraining your algorithms and choosing your parameters wisely is important. And afterward, you can play around with this some more. And inside the Hoggleslog library, there are additional distance functions you can try out and play with and make your own. It has a kind of a similar framework if you're into that. So once we've identified all of our objects, then what we generally do at this point is match them with our observations using a similar technique to doing the tracking. Then we extract all the data from all the other model variables that we have available. And so we have these spatiotemporal model storm objects with all these attributes, so in nice computer readable format. So now we can throw the machine learning algorithms at it and see what they can predict. So we're going to import some models from the scikit-learn library. So we have the linear regression, good old linear regression. Random forest is one of my personal favorite algorithms. For some additional stuff, we're going to do kernel density estimation, which I know a lot of people are big fans of in the meteorology community. And then normal distribution, because it's the go-to one. So first we want to load all of our data in. So we're using pandas and some fun inline stuff to load in a whole bunch of CSV files at once. And it actually goes pretty fast. We also have all the variables that we loaded in. So for all the storms, we have centroid, latitude, and longitude, updraft velocity information. But we also have, we have like time changes and things like that, radar reflectivity, updraft speed, downdraft speed, LCL, 0 to 6 kilometer shear, and you can kind of scroll through them on your own if you want, and lapse rates and things that might be important for making hail forecasts, essentially. We can also kind of plot a histogram of our hail sizes and make sure they actually look reasonable. They do. The ones that are in the 0 bin are ones that weren't actually matched up with an observed storm. So we can train algorithms to try to pick which ones actually were matched and which ones weren't. But for now, we just filter those out, and we want to just train one to find the hail size, assuming that the storm is going to produce hail. And so our first method of doing this, the usual go-to one, is let's make a linear regression. Let's do MOS. And let's make our fit. So this example is interactive, but we fit a basic linear regression between updraft helicity on the x-axis and hail size on the y-axis. The green line is just a straight linear regression. The purple line is a power law relationship, so you take the log of the hail size and the log of the updraft helicity, and you can get this nice little curve, which depending on how your data is oriented, may be a better fit. But one thing you'll notice that while there is kind of this slight positive linear trend, there's a lot of variance at a particular updraft helicity threshold level, which kind of makes sense because we're looking at like 24-hour hail forecasts. So there's going to be some uncertainty in how the storms are matched, how the storms in the model evolved versus what happened in real life. And even within the life of the storm, sometimes the storm only produces really large hail for a very short period of time in its lifetime, and the rest of the time it's producing like pea-sized or whatever. There's different cycles and all kinds of grid scale things going on that we're not modeling correctly, and that aren't captured by abstractologicity for that matter. So the question is, how do we add that information in and try to make a better prediction? One way is we could add more terms to our linear regression, which is a pretty traditional approach. The problem is actually picking out those terms when you have a lot of data and a lot of variables can be very slow and time consuming. And one other problem with linear regression in general is that you're just making one global fit. It doesn't account for different situations, different times, different weather conditions, different scenarios particularly well. But there are other methods out there that can actually take advantage of this additional information and give you improved predictions. One of these is called the random forest. It's kind of a short, you can read a little bit more about here, but it's basically an ensemble of what are called decision trees. So a decision tree is just like if temperature is greater than 50, do this. If not, do this. And you can build these automatically based off of a whole bunch of data, and there's a lot of cool algorithms out there to do this. Random forest makes an ensemble of these decision trees and basically add some randomness into the growing of the trees to make them a bit more diverse. The idea that so once you have like slightly non-optimized trees, but each one can explore a different part of the phase space or the domain and come up with different predictions. And then you can average the predictions together and get a unified a mean. You can get standard deviations. You can get a whole PDF just from these predictions. And it does variable selection on its own. It's robust to outliers. It's shown a lot of accuracy and a lot of power in a lot of different applications. And as far as these complex machine learning algorithms go, it's pretty easy to use. All we do is we call the random forest regressor class, tell it how many trees we want, how big we want to grow the trees, and we only want to sample a square root of the maximum number of features. We don't just kind of speed it up. Then we just fit it, pass it the data. We'll give it almost all the data except for like the ID number, and fit it to the hail size. We also filter it based off get rid of the hail sizes above 100 and the ones below that at 0. And it runs, and that was fast. And I was just running on my laptop. So it's a pretty robust algorithm, and depending on your data size, it can actually run pretty fast, and it parallelizes. So you can throw like 1 million cases at it, and it'll train each tree separately on like a supercomputer or a computing cluster, and you can get really good big trees that are really powerful and do cool things. Other cool thing you can get out of random forest is what's called variable importance. So we want to. The random forest may seem like a black box because it's all these trees doing stuff, but it does provide some diagnostic information to let you know what's going on. This statistic basically measures how much error is each variable decreased. How much does the error in the training predictions go up if the random forest if you randomize a particular variable and then throw it back into the random forest. And basically, so if randomizing doesn't do much, then it's probably not being used very much, and it's probably not very important. Whereas if it does have a big impact, it should have a high importance score. So what we can see from here is that the top feature is the abstractologicity. Also the centroid latitude, so where the storm is located, makes a difference. The 500 millibar moisture distribution has an impact. LCL. I mean, some of the things that are coming out actually kind of make sense in the context of predicting a hailstorm if you're looking at it more from a physics-based approach. And this little slider, we can look at the top 10, we look at the top 25. You didn't look at all of them, or we can look at most of them. And the names get really small, but you'll see that even some of these like random blue variables still have a slight impact, although it's less than 1%. So the ones above 1% are like the top 20 or 30. So one thing you can do with this too is also filter out variables that may seem not to be very important and may actually contribute noise to the problem. So then we actually want to validate. So we trained all of our data on data from May 20th through June 3rd, and we want to predict for June 4th, which is all the examples that we're using. So run our predictions. We get these scatter plots. So here's a linear regression. Here's the random forest. The one thing you'll notice is there's still a lot of spread in the random forest mean predictions, but what it does better is it actually is predicting like higher hail values. And some actually do hit the mark. Some are still a bit low. But yeah, we get kind of, the RMSEs end up being pretty similar. There are some definite differences in the prediction characteristics. And finally, we can do a little bit more exploration of this by looking at the full distributions of the random forest predictions. So I had this, so loaded in, we have this little slider. This is looking at a subset of the prediction. So we kind of notice there's kind of these two peaks. So if we slide over to the bottom part of the distribution, we see that there's a group of storms that have a high probability of having hail between like 10 and 40 or 50 millimeters. So say like half an inch and 2 inches. So like in your possibly severe to not just below significant severe. But then when we look at the upper end of the distribution, we notice that once it gets there, we kind of have some that the means are more like above significant severe, and there's actually a not insignificant chance that there may be some baseballs or golf ball sized hail associated with these storms, which is useful if you're a severe weather forecaster and you're trying to get these long tail probabilities and try to figure out, should I be warning people for these more intense stuff? And by using a more non-parametric approach like random forest, you can actually pick up on some of this information. You also notice with these stronger hail, there's also still a not insignificant chance of there just being 1 inch hail or smaller hail. So it also captures the fact there's a wider spread when you're dealing with larger hail values, and that these storms that do produce larger hail often also produce smaller hail. So we're capturing uncertainty. We're showing it in kind of an interactive way. This could be potentially useful for a forecaster who's trying to figure out, how should I warn this event that's coming up in the next day. And these techniques aren't just applicable to hailstorms. You can do this for any kind of prediction in random forest. And so we throw all kinds of different stuff. So kind of to wrap up, I want to show you some cool tools. There's some additional resources and links at the bottom of the page. Scikit-learn has really good documentation explaining all the different machine learning methods and examples and how to use them, and the API. Also, a scientific Python lecture series that's pretty cool. If you want to play around with some big data and try out some cool stuff, there's a site called Kaggle. So it's a data science competition site. Basically, companies will post big data sets and want you to try to predict something with them. And sometimes they'll give you lots of money. Like if you can solve diabetic retinopathy, you can get $100,000. You're competing with a bunch of people all over the world. So at the very least, in addition to the more advanced stuff, they have some more basic 101 kind of problems. If you just want to try some canonical data science problems and play with some basic methods. And there's forums on here and lots of different ways to kind of get up to speed on different methods and see what the latest and greatest stuff is out there. And people even as part of it, after every competition is complete, the winner usually has to open source their code and write a blog post explaining how they did it. So it's a great place to get new insights. In addition, not only is the general community on there, weather does pop up sometimes. So we recently had the How Much Did It Rain contest on Kaggle. Basically giving you a bunch of radar data and having to predict if it rained or not, or how much it rained, and actually predict a distribution of rainfall amounts. There will be a second part to this coming up in the fall. I don't know exactly when, but it'll be coming up soon. So if you're interested, or you want to give your students a project, like a semester project for them to work on to try to learn some more about machine learning or computer science or programming, this is a great resource for them to try out. There's also some older content, even though the contest is over, you can still go and download the data and test it on the website. So you can still make a submission and drop it in, and it'll score you, and you can see how you did. So with that, are there any questions, comments before we break off for lunch, and I think we still have a few minutes left.